Welcome. We want to take a look at an example of determining if a function is one-to-one, and we're going to use the graph to do that. So this is just kind of an introductory, do we get the idea of what it means to be one-to-one? If we actually want to verify that a function is or is not one-to-one, we should verify algebraically that it is, or give a specific example of why it is not. Those are the truly acceptable ways for justification. But to get the idea, we can look at the graph. So use the graph of the function to decide if the function appears to be one-to-one. G of x is given by x squared minus 2x. I am using GeoGebra, that is geogebra.org is the website, to graph our functions here. So our first one, g of x, is x squared minus 2x. Here it is. I'm going to click right here. Usually it appears right away, but I have presented it, wanted to hide them at first. So does this function appear to be one-to-one? Well, we need to remember what it means to be one-to-one. A function is one-to-one if each element of the range is associated to exactly one element of the domain. So for example, 8. 8 is an element of the range because g of 4 is equal to 8. So then the question is it associated to exactly one element of the domain? So we've already said it's associated to 4, but is 4 the only thing it's associated to? Well, unfortunately not. We can see here at -2 that g of -2 is also 8. So there's two elements of the domain, namely -2 and 4, that are associated to that output of 8. So it is not one-to-one. If you wanted to just kind of observe that, we can plug in here x equals, I'm sorry, not x equals, but y equals 8, and that's going to give us that horizontal line, and we can see those intersection points. So very nicely here, what I like about GeoGebra, if you're not clicked on any line, then you can click on it and hover over those points. Let's see here, try that again here. It should click on it. It gives an intersection of two -2, 8, and an intersection of 4, 8. So we can verify that those truly are the points of intersection there. So we can respond to the problem in this way. We can say that the function is not 1-to-1. For example, g of -2 is equal to 8, but that is also g of 4. So we have two elements of the domain associated to one element of the range. That is two elements of the domain, -2 and 4, are associated to one element of the range, 8. So it's not one-to-one. I made my decision. I gave a brief justification, but I also referenced the definition of one-to-one just to be clear, right? This implicitly references the definition, but I did a little bit more explicitly here by writing it out. We also want to consider f of x, which is 2x plus 1, divided by x minus 1. So if we go here, I'm going to hide this again and hide that, and grab onto our function f. And does the function appear to be one-to-one? Well, I can pick out elements of the range. So again, here I can see that the function is equal to 8. Let's see. Oh, it doesn't tell me that intersection point now. That's a little bit strange. That's okay. But I can see that it is equal to 8 here at, what is that, 1.6 something or something like that. The question is, are there multiple elements of the domain that are associated to any individual element of the range? And it looks like if I were to plug in here, maybe y equals 2, well, I don't see where it actually says that there is an intersection. If I were to say y is equal to 2.1, let's see, do I get an intersection there? It is not telling me any nice, convenient intersections anyway. Uh, but it actually does work out. It's kind of hard to see at this point because we get this idea of horizontal asymptote that we'll also discuss later. But it actually works out that there are no outputs associated to more than one input. So it is one-to-one. I can't find anywhere that it looks like I have two inputs associated to one output. So here we can simply say it appears to be one-to-one. It appears to be. Do I have an official way of saying, oh, hey, look, I don't get any, right? No matter how far left I go and how far right I go, I can't see all of that stuff. Do I have a formal way of saying using the graph that when I extend beyond what I can't see, I don't have any intersections? No, right? That's why this idea of looking at the graph is not sufficient when, especially when we cannot view the entire graph. So graphs are a good way to understand, but they're not necessarily a good way to justify. So we want to have good, more formal methods for that, which we'll take a look at in following examples. But again, in this case, we saw the examples of both a function that appeared to be one-to-one and a function that appears to not be one-to-one.